Hello and welcome to our webinar. Today we are going to compare Moxy to competitive devices. Our format for today will start off with a bit of background on the competitive devices. Then I'm going to do a short demonstration with the blood pressure cuff occlusion. And then we're going to look at the technical reasons for the differences that we see in the demo. We'll have a Q&A at the end of the session, so if you have any questions, be sure to type them into the question panel, which is on the right side of your screen. The webinar will be a little bit on the shorter side today, so we're aiming for about 30 minutes, so just so you know what to plan for. So with that, I'm going to jump into the slide presentation. Okay, so our topic is Moxy comparison to competitive devices. The competitive devices that we know of that are really playing in this space, and here I'm really talking about devices that are playing in the athletic market. So we have the Moxy, we have the BSX Insight. I think everyone is pretty much aware of that. We want to make some comparisons to the Artenis Portamon device, and then there's two other devices that are still in development that we expect to be on the market sometime either in 2017 or 2018, and that's the Human device and the Oxy 4 device. So if I talk a little bit about the pricing here, just to kind of give a little bit of perspective on this, the Artenis Portamon is the oldest of all 5 devices. It's been on the market the longest. It was probably on the market about, I don't know, maybe 7 years or so before the Moxy. That device sells for around $10,000 to $15,000, including their software. And it really doesn't do, it has some additional features, but it really is basically the same thing as what the other devices are doing. Next in line is probably the Oxy 4 device. They've inkled on their website that they expect the sell price to be around $3,000 per unit. Now they're promising some additional metrics, which we'll see if they're able to deliver on, but that's kind of what they're targeting. Moxy is probably next. So Moxy with software sells for right around $1,000. Then I'm thinking the BSX is the next in line for price. The BSX we've seen anywhere from $200 to $400. They offer a couple different models for whether you want running only, cycling only, or dual sport. I haven't seen any pricing on the Human yet, but I expect that it'll probably be the least expensive of all of them. It'll probably be around the pricing of the BSX, or maybe even a little less, just based on what I'm seeing of their other marketing materials, but that's really just speculation at this point. The target market for the devices is a little bit different. Artenis is definitely targeting researchers, and they kind of got pulled into the sport market. I don't know that they really intended to go there when they launched that device, but that it was the first portable device that really had any practical way of being used for sports. So that's where it's been used to some extent, but it really wasn't designed for it. It's not completely sweat proof, and it has some other limitations. For Moxy, we're definitely going after the training centers and the high-end athletes is kind of the target we're shooting for. Oxy 4, it's not perfectly clear to me who they're going after. They seem to be going after, based on their price point, they seem to be going after more of a researcher or a very high-end training center with the price point that they're looking at. And then the BSX and the Human both seem to be targeting just individual athletes. That to some extent, they seem to be trying to bypass the trainer and get the athlete training advice directly. So a little bit different in market focus on those. The training methodology is also something interesting to talk about. So Artenis really doesn't have any training methodology whatsoever. They don't really try and promote athletic training at all. With the Moxy, our training methodology is that we help people diagnose what's limiting their performance, and we help guide their training in real time. We've really stayed away from the lactate threshold. With both the BSX and the Human, initially both of them were very strong in targeting the lactate threshold as an application. So that was kind of their training methodology, was to calculate lactate threshold. We've seen both of them drift away from that pretty substantially since they launched. In fact, like the Human on their latest marketing literature that I've seen, they don't show anything related to lactate at all. Or the earlier literature was all about lactate. And BSX has also moved away from that. They used to call their device a lactate threshold monitor, and now they call it a muscle oxygen monitor on their website. So we see them kind of moving in our direction from a training methodology perspective. It's not really clear what Oxy 4 is going to do from a training methodology, but we've seen images on their website that show very clearly that they're doing a 5-1-5 test. So clearly they are getting some influence by what we're doing with Moxy as well. The SMO2 accuracy, that's actually what we're going to talk quite a bit about today, is very different between the Moxy and the other 4 devices. So all of the other 4 devices, at least as far as I can tell today, are using a similar methodology to calculate their oxygenation parameters. And whether they call it SMO2 or not, you know, that you can quibble over the terminology. But they seem to work in a way where they don't really have useful accuracy on a scale of 0 to 100%. And the Moxy does have useful accuracy on that scale. And so that's really one of the primary functional differences among these devices as far as how they can be applied for athletes. So now I'm going to attempt to do a demonstration. We'll see how this goes. Doing a live demo is always a little bit risky, but we'll see. I'm going to convert over and show parapedal. So there, hopefully, we're seeing the parapedal screen. Let me make sure. Yep, I'm going to move this off to the side a little bit. Okay, so we should be seeing the parapedal screen. We've got the Moxy sensor shown on the top row, and we've got a BSX Insight sensor shown on the bottom row. And the green is the SMO2, and that's what we're going to focus on for today. So I've got a blood pressure cuff applied to my upper forearm. Let me make sure we can see that. Yeah, I think we're in the camera view. So I've got the blood pressure cuff applied to my upper arm, and then I'm going to be measuring on the forearm. And right now the cuff is deflated, so I'm just at rest, and I'm going to take the first measurement here with the BSX. Now, it takes the BSX about 20 to 30 seconds for it to get the first reading, so we're going to have to wait just a little bit for that. And I'm not sure why it takes it that amount of time. I don't know if they're doing some averaging in their algorithm or what the limitation is there, but it typically seems like after I place it on the tissue, we've got to wait about 30 seconds to get that first reading. So there I'm getting a reading on the phone. We'll see when it's there. Now it's showing up on the screen as well. So now the BSX is reading 79% saturation, which is a perfectly reasonable number for me being at rest. This is on the high side for what I usually measure for me, but I was doing some practice with the cuff before, and that's going to elevate my readings. So at rest, we're seeing a 79% with the BSX, and now I'm going to put the Moxy on here. Give it a couple seconds. So the Moxy, we're seeing something similar, 73, 75%, jumping around a little bit. And this is, again, exactly what we would expect to see in this case. So now for the demonstration, I'm going to inflate the cuff. So I'm going to close off the cuff here, and I'm going to pump it up. I might as well measure while we're doing this. Let's see if that works. So, and I'm going to pump this cuff up pretty far. I'm going to go up to about 250 millimeters of mercury, maybe 260 or so. My cuff leaks a little, so I'll have to keep pumping it up. And so I should pretty much completely stop blood flow. And we're seeing, so I've got the Moxy sensor on there now. We're seeing that number start to trickle down. Now, I'm not doing any exercise right now, so this is going to trickle down pretty slowly because even though I've stopped supply, I really haven't increased demand much. So this is going to go down slower than if I were even doing an isometric exercise. But then, just so we can see the numbers here, we got to get that BSX a chance to take a reading. So I'm measuring in the same spot with the BSX device. And we'll give this, it takes about 30 seconds or so for it to for it to start to take a measurement, so we'll give that a little bit of time. Make sure I keep this pumped up. There, I'm getting a reading on the phone, and there now we're getting a reading on the parapedal as well. So you can see, you know, in the time that the Moxy had dropped, the BSX now has only gone down to about 65. There, it's down to 64%. So a little bit of a muted response. And I'm just going to toggle back and forth between the two here, just so we can see this oxygenation continue to trickle down. So there, the Moxy is still going down. We're about 25 right now, 23, 22. So the readings on the Moxy are still trickling down. They bounce around a little bit, but you can see it's 21 now. It's starting to get tingly in my hand. You know, I can feel the effects of the blood pressure cuff starting to take effect. And we'll go back here to the BSX again just to see where that's at. Unfortunately, it takes a little bit of time for that to come up with a reading. Again, I'm not sure why that is. There must be some part of their smoothing algorithm that just takes a while to get filled up. Oh, and by the way, while we're waiting for that, I wouldn't recommend doing a lot of this blood pressure cuff work on yourself, especially with this high of occlusion pressure, and for this duration of time, you got to be careful that we don't hurt anything. So if you do want to do this, make sure you're very careful with how the cuff is applied, and don't leave it on for too long. See, so now the BSX is reading 68, which is actually even a little bit higher than what it was before, and it just doesn't have the dynamic range that we see out of the Moxy. So I'm going to go back to the Moxy and see if we can kind of watch things approach zero here. Yeah, so now the Moxy's down to about, we're getting down to the single digits, 9, 6. We may even see it bounce down to zero. When we get to the very low end, things tend to be a little bit more noisy. They tend to be a little bit more sensitive to inhomogeneities in the tissue, and so on. Now that Moxy's starting to read 2, and so it's not quite as stable as what it is when it's up higher, but we're getting right down to 0, and this is what we'd expect to see when you apply a tourniquet to the arm and aren't letting any blood flow in. And it's really starting to get tingly now. I can really feel the effect of the cuff. We'll go back and measure with this BS6 one more time. Kind of show what it's measuring. So maybe take 1 or 2 more measurements here, and then I'll release the cuff, and we'll look at what happens when the cuff gets released. Give this a couple of seconds to get a reading on the BSX side. I'm still at about 240 millimeters of mercury. Yeah, so now the BSX is reading like 64, so it really 63. It really seems to have reached its low plateau, kind of in the 60s, you know, so definitely not anywhere close to 0 like we'd expect it to be. And I don't know if you can see it all. If you can look at the difference in color between, I don't know if this shows on the camera. You know, we definitely are deoxygenated. My left arm is you know, clearly turning blue. If I would leave this on a little bit longer, the skin would deoxygenate some more, and it would even turn a little bit more blue. But you can definitely see the difference in color between the limb that has the cuff and the limb that does not. But then I think I'm getting tired of this, so I'm going to go ahead and release this cuff, and we'll watch the recovery on the BSX side. And so the BSX is popping up nice there. And this is what we'd expect. We'd expect to approach, you know, get somewhere close to the arterial saturation. And now you can, I don't know if you can see this on the camera, definitely my left arm is very pink. It's almost bright red compared to my right arm, and that's because we just let all of it got very vasodilated from having that cuff on, and now it's just getting a surge of blood flow with all of that oxygenated blood flowing back into the arm now that cuff is released, and it feels much better than what it did when that cuff was applied. So there we're peaking out about 82. I want to quick get a reading from this Moxy and see what it looks like in the similar situation. Yeah, so there the Moxy's reading a kind of a similar value in the 80s or so. We may have missed the peak of that hyperemic response. It's probably on its way back down just a little bit by now. Well, maybe it's still going up, 84. Right in there somewhere. So this is what we'd expect to see. We expect to see get pretty close to 90, maybe even into the 90s once that cuff is released. But this is really the point about SMO2 accuracy that I want to talk a little bit more about when we go back to the presentation. So I'm going to take this cuff off, and then we're going to go back to the presentation and talk about why the Moxy is able to do that, but the BSX and the competitive devices don't. Much better. Set that aside. Okay, so we'll go back to the PowerPoint presentation. And now we really want to focus on why this is. And just a reminder, if you have any questions, please go ahead and type those into the question panel on the right side of the screen. So there we go. Okay, so what's different about the Moxy algorithm compared to the others? And there's really three issues. The first one is that the Moxy assumes that the tissue is in layers. The second one is that the Moxy uses a much more sophisticated optical model that allows us to accommodate the tissue being in layers. And the third one is that there are some very specific design elements in the Moxy that really aren't obvious from the outside, but they enable the accuracy to actually be realized when measuring on tissue. So we have to make that optical model match what we're really measuring on the tissue, and that requires some specific design elements. So I'll go through those a little bit too. So first of all, the issue of layered tissue. The Moxy assumes that the tissue is made up of 4 layers, which are epidermis, dermis, adipose, and muscle. So epidermis is the most shallow layer of skin. It's less than a millimeter thick, and it's where all the melanin is. So if you have darker colored skin or lighter colored skin, it's all because of the epidermis. That melanin really doesn't go down. There's a little bit in the dermis, but not much. Most of the skin color that you see is way up at that shallow level. The dermis is just the rest of the skin, and it's where there's blood. Well, the blood flow in the skin is mostly in the dermis. So when you get hot and your skin turns red because you're warm, it's the extra blood flow in the dermis that you're seeing there. The adipose layer is the fat layer, and adipose, I don't know why, it's just a fancier name for the fat layer. There's very little blood in the fat layer. It's mostly just kind of white material. When you look at the fat on a steak, that's essentially what we're looking at here. Very little vascularization, but it varies widely in thickness. So we see a big range in thickness from person to person, and that's one of the big confounders, one of the really challenging attributes for measuring accurately is being able to accommodate a wide range of adipose thickness. Then the lower layer is the muscle layer, and that's of course the layer where the action is. That's where we want to get the information from, but we got to be able to get through those other 3 to get the information from that muscle layer. Now part of this diagram is really important to consider. When you see that the light travels through the tissue, but not nearly all of the light actually goes down through the muscle layer. Some of it only interacted with the superficial layers, and this makes the calculations much more challenging because you need to know how much of the light interacted with the muscle layer versus how much interacted with those other layers in order to be able to determine what's going on down deep. So the next issue then is how do we make use of that? How do we take that layered information and actually turn it into something valuable? And we use an optical model for modeling how light propagates through all of those layers. And it's pretty complicated, but you can it actually the root of it is fairly simple. if you think of the Plinko board, this is a picture of the Price is Right Plinko board. When they drop the disk at the top, you can think of that disk being like one photon of light. And the disk drops down, and then it hits a peg on the next row, and then it has a 50-50 chance of going left or right. And then it drops down to the next row and has a 50-50 chance of going left or right. That's kind of a one-dimensional model where that photon could either be scattered left or right as it travels through that Plinko board. Well, the same thing happens with light as it propagates through tissue. That photon can travel some distance, and then it's going to hit a boundary, like the boundary of a cell wall or different parts of the cell. They have different indexes of refraction, and that causes that photon of light, they call it, to be scattered, and so it goes off in some direction, and we model that as a random direction. So we model the photon going a certain distance, and then it gets deflected at some random angle. And then we model a whole bunch of photons, and then we determine how they travel through the tissue. In order to do this, we have to model hundreds of millions of photons, because most of them don't actually make it to the detector in the model. We can't tell at the beginning the photon, how it's going to zigzag its way through the tissue and end up hitting the detector. So we literally trace hundreds of millions of photons, and this takes days on a very high-end computer to do all of this complex modeling. And then we model different fat layer thicknesses and different optical properties in the different layers to be able to accommodate the range of conditions that we expect to see on real athletes. Then once you have that information, you're nowhere near done. Now you need to do some fairly significant math, and that's the equation down at the bottom. And this is it's not that pleasant. I mean, it's actually fairly complicated to work through this. We've got a bunch of sums, we got some exponents and things like that. But that is how we model a ray that has traveled through the tissue, and it's getting absorbed differently by the different colors of the tissue it travels through. This is the math that we have to solve in order to create that Moxy algorithm. So I'm not going to derive that. I'll spare you guys that, because that would take a long time. But this is really the secret sauce of the Moxy, and how we get that to work, how we're able to measure accurately. So I'll go on to this is, I think, my last slide here. We've got this optical model drives us to certain design elements in the Moxy sensor. So the top picture on the right is a cutaway view of the sensor. It's like you slice the Moxy right in half, right through the optodes. So the first design element that's important is the fact that we have these optodes, and really what these are, those are those gray lines that you're seeing kind of right where the optode lines are pointed to, kind of right here. Oops, that isn't what I wanted. Right here, and right here. And these are actually just clear plastic rods, and they're coated with a cladding that makes them be fiber optics. So they're able to guide the light either from the LED down to the tissue, or from the tissue and back up to the detector. And one of this, I'm looking at the lower right picture now. One of the really important attributes of these optodes is that light that is more normal to the tissue, more perpendicular to the tissue, will travel up the optode. It'll bounce off the walls and it'll make it to the detector. But light that is at a wide angle doesn't. It passes through the wall of the optode and gets absorbed by the sleeve that is mounting the optode. And that prevents the wide angle light from hitting the detector. So this is one of the things that helps us be insensitive to the sensor coming just a little bit off the tissue. It doesn't get us in trouble as fast under that condition. And it also gives us a really controlled, we know exactly where the light came from that ends up getting to the detector. If you just have a window, then the light could have come in at a lot more different angles. And so this is one of the critical features for making the sensor match the model so that we can take accurate readings. Another attribute, another design element is that the Moxy uses 4 wavelengths of light. So it uses 4 different colors of light. And they're from the very edge of the visible spectrum at 680 nanometers out to 800 nanometers where your eye really has no sensitivity at all. And this picture here with the green square with the brass colored circle in the middle, this is actually a photograph of those of the emitters, of the 4 LEDs. So each of those little squares in the middle is what glows when we run current through it, and that's what produces the light. But this is a custom designed element. This is made specifically for the Moxy, and there's several reasons we had to do that. One is because we wanted those 4 particular wavelengths, because that allows us to be insensitive to melanin and be maximally sensitive to the hemoglobin and myoglobin and things like that. But then it also allows us to put them very, very close together so that when we shine that light into the emitter optode, all of that light goes into the tissue at the same point. And that's pretty critical for making the sensor match the model as well. Another one is the send to receive spacing. So that's the distance between the emitter and the 2 detectors. We use 12.5 and 25 millimeters, and that is important for helping us reject the skin. We want to be as maximally sensitive to the muscle layer as we can and minimally sensitive to the skin, and that's one of the attributes that helps us do that. Another one that's important is that we use 1 emitter and 2 detectors, and there's some. If you study that mathematical equation on the previous page and you learn what it's telling you, it tells you you should use 1 emitter and 2 detectors. And when I see devices, I don't know if you can see this, like the BSX device, it has 2 emitters and 1 detector, and that tells me that they do not understand the equation on the previous page. It has to do with the stability of the LEDs and some other important complexities, I guess I'll say it that way. But that's a design element that is built into the Moxy, and if you are not familiar with some of those features, you maybe wouldn't realize that that's important. Another feature in the Moxy that I'm not sure if the competitive devices are using or not is temperature compensation. So one of the problems with LEDs, and it's just the nature of their physics, it actually gets down to the physics that they use to produce light in the first place. The color of the light changes with temperature, and that changes the calibration of the device. It changes its ability to act as a spectrometer. And with the Moxy, this is another feature of that LED mount, is those 4 LEDs are mounted on one big brass plate, or that brass disc, and that, because brass is there's copper in the brass, that makes it a good thermal conductor. So all 4 of the LEDs are at the same temperature all the time because they're mounted to this nice metal mount. And then we can also sense the temperature of that metal mount, and we can then accommodate any variations in the color of the LEDs. So whether a Moxy is warm or cold, it's still going to measure accurately, and that's pretty important when you're dealing with, like, people might be in a swimming pool or coming out of the pool, or the athlete might be wearing it under clothing where the sensor warms up a lot. A lot of those things are important to deal with. I put the detectors up there. We have some fairly low noise detectors, and the detectors are also they have sensitivity over the range that we need them to be sensitive over, and that again gets back to our wavelength selection, and our ability to reject ambient light is important with that. And then the final one I'll talk about is again a bit technical, but it's the analog to digital converter in the Moxy is something that I don't think the competitor devices, at least the ones where I've seen the pictures of the insides, I don't think they're attacking this quite the same way that we are. The analog to digital converter that we use is the single most expensive component inside the Moxy, and it's what takes this super low level current from the photo detectors and converts it into a digital signal that we can use to do calculations on in the microprocessor. And that there are some, again, if you go back to the equations and you understand what's important in those equations to take accurate measurements, you can convert that to what's important to have in an analog to digital converter. And we've done that work. And so we can show, we can show that our analog to digital converter is very highly linear. It has very little channel-to-channel crosstalk, and various other parameters that are really critical to measuring accurately. So with that, that's the end of what I had for a presentation. I was aiming to keep it short. I hope I did okay. With that, I will open it up to questions. If anybody has any, please type them in. I see there's a couple here. Okay, no, just a comment. I'll give you just a few more minutes, or a few more seconds, if anybody has any questions. I realize this might not be the most chattable topic that we've ever had, but I just wanted to give you some information so that when people ask about the competitive devices. Oh, I should comment too, just while we're waiting for a few more, see if there's any questions. One other comment is that, as near as I can tell, all 4 of the competitive devices have those same limitations. So when I went through, and I went through how the Moxy works, and I went through some of those design features, I think all 4 of them, with the data I have now, and I don't know for sure, I haven't, of course, the ones that are in development I haven't tested, but I think they will all have similar issues to what we showed in the demonstration, where they, at least in some cases, they won't be able to measure with useful accuracy on that scale of 0 to 100. So if you did if you do an occlusion and we expect to see a 0 and they're showing a 60, it's hard to know that 60 is really a low number. That's where things can get confusing. One question here. What about location on the body? That is that's very important. And that's one of the things that the Moxy algorithm allows us to be flexible with. So because we can handle the wide range of fat layer thickness, we can go over a wide range of body positions. But with the Moxy, it is based on a layer of skin, fat, and muscle. So measuring on a skull, I don't know what's going to happen. It's not designed for that. So we want to be on a muscle location. The fat layer thickness does need to be less than about 12.5 millimeters. Otherwise, we just don't get enough light from the muscle in order to be able to take a valid reading. So we can measure, anywhere where you're within those conditions. I haven't. Somebody's asking about is the BSX still calf only? I've only seen that they have a calf mounting device. I haven't seen that they mount other places. Besides the calf, some of the other, like the human, the photographs they show it on the vastus lateralis. So we may see the human trying to go to other positions, but we have seen data where people have been using their BSX on different muscle sites. But again, with the fat layer thickness variation, they just don't seem to be able to accommodate that well. And then one asks here, the Moxy is also specifically curved. That is an interesting. I'm surprised that's an interesting question. The Moxy does have a curved shape to it, and it seems logical to me to do that because it makes it sit nicer. And when it's almost any place you measure, the tissue is pretty much has some curvature to it, to where this would be helpful. It may not be perfect in all cases, but it seems like the general trend, the sensor would be more stable like this. We see all the other sensors we see, they're more flat. And not sure exactly why they do that, but that is mainly just a mounting assist feature. Another question, what about ANT and Bluetooth? That is a really good question. So right now the Moxy is ANT Plus only, which prevents us from communicating with Apple devices. That is a limitation of the Moxy. I think the BSX does ANT, and it has some Bluetooth capability, but there is no Bluetooth standard for muscle oxygen. So I think it only communicates with its own app. I don't think it communicates with other devices like Apple or Polar, outside of its own app. And then I don't know what the other devices are going to do. I think Human does indicate they're going to do ANT. I imagine Human will do Bluetooth as well. And I have not seen with the Oxy 4 what they're going to do. The Artness Portamon only communicates with its own software. It's not an open communication protocol. Another question, is the THB value accurate? That's another good question. That in all cases that I'm aware of, the THB value is only an indication of whether it's going up, down, or staying the same. And it's just a measure of blood volume under the sensor. And so the Moxy does the same as the other devices in that case. So essentially the THB on the Moxy acts like the SMO2 does on the other devices, where it'll go up when it's supposed to go up and down when it's supposed to go down, but you really can't make a whole lot of use out of the number as an absolute value. Let me see here. One more question. Do we need the higher hertz of the Bluetooth? No. The Bluetooth in some cases could have a higher communication rate, but there's really no need for that. Even at the highest update rate for the Moxy, it'll update 2 times per second. The ANT still has the ANT updates 4 times per second, so we still aren't exceeding the ANT update rate. And even if we were to go faster, we'd still have room. There's ways we could go even faster with the ANT. So there's really no limitations for update rate as far as the communications are concerned. Okay, I think we've got to the end of the questions here. So thanks everyone for attending.